Okay, so let's go. Oh, shoot. God. Oh, sorry about that. Oh, my. All right, me and my touchpad. Let me get my trusty mouse over here. I'd work much better with a mouse. All right, let's see what happened. The acceleration, that's about what I came up with, I think. All right, but then if you look at the acceleration, my gosh, that's huge. But then look at this guy down here, 10 to the 17, 4 orders of magnitude, or 3.5. The magnitude of the force is the same, but the direction is opposite, and the acceleration is humongous for an electron. All right, so here we go. Now, if something goes into, if a charged particle, here we are working again with electric, goes into this parallel plate capacitor. All right, so remember, there's a uniform magnetic field. It's like it's flying into an Oreo cookie. Here's the two cookie wafers, and the frosting in the middle is the electric field that it can easily pass through. All right, and it hits that electric field and it feels the force. It goes, well, what happens to something that looks like this? What happens to something that's traveling like this and then hits a force that's going this direction? It's got a velocity, and that force stays with it. Well, yeah, it's going to go in a circle. It's going to curve. Now, and so therefore it's going to accelerate. But how's it accelerating? By changing direction. Remember, you've got 3 accelerators on your car. You've got the gas pedal, which you can push on to speed up. You've got the brake, which you can push on to slow down. And you have the steering wheel, which you can use to turn, which accelerates you towards the center. Remember that? Centripetal force by changing direction. Okay, so there's a force. And what did we say that was? We said the force of the centripetal force is equal to the mass times the acceleration caused by the centripetal force, which is equal to mv squared over r, which is the radius of this thing, which now, but wait, we also got this magnetic force, which is equal to qvb, which is equal to the magnetic field force, which is acting on it. That's the big idea behind the mass spectrometer. Fire the thing into an electric field, get it to turn, curve, and when it curves around it, bam, it's going to hit a detector. Watch this. Watch and learn. Okay, so here it comes. A velocity selector. In other words, now this is kind of interesting. We've never thought about that. We've never done this before. Now look what's happening. Got it going into the paper. So this is going into the paper. It's an ion flying this way. Okay, so into the paper, velocity is this way. So it's going to feel a force that's up. All right. Into the page, magnetic force, velocity going this way. Do the right-hand rule, boom. It's going to feel the force that's going up. However, so what kind of electric field do I need to put in here? If it's an electron coming in here, I want it, and it's getting pushed up, I want to be able to push it down. So I'm going to put a bunch of negative charge down here. So I'm going to have an electric field coming down this way. But that's not what they did. What are they doing to us? Why is this in here again? The electric, oh, I see what they're showing us. The electric field that's just what I showed you. So now, here's what I said. Here's all the stuff that I put in here. But they don't show us the velocity selector, how it works. How should an electric, okay, so it's going to be coming down. All right, they just wanted to answer it that way. The magnetic force cannot do work on a magnetic field. Ooh, great conceptual question. Why? Why? Because what is work? Force times distance parallel, not perpendicular. It's perpendicular. But here's what we did. Here's how we do a mass spectrometer. So here we go. The figure shows, oh, we might start with this. The figure shows the bubble chamber tracks from an event that begins at a point A. Okay, at this point, a gamma ray travels from the left, spontaneously transforms into two charged particles. Okay, these particles move away from point A, producing two spiral tracks. A third particle is knocked out of a hydrogen atom and moves forward, producing the long track. Okay, the magnetic field is directed out of the paper. It's coming at us. Electric field coming at us. Determine the sign of each particle and which particle is moving most rapidly. Which one is going the fastest? Well, here's the equation for R based on my analysis earlier that I showed you. So the one with the biggest radius is going the fastest because look, V is up here. The one with the, okay, or the one with the most, could be the one with the most mass has the biggest radius. Because if it's got a huge mass, it might just keep going straight too. But we're going to assume all of the charges have the same mass. So if this one's going, if it's coming at us, the force is going down. So A is negative, B is positively charged. Particle 2 is a little bit fat. Particle 3 is the fastest one. All right. Oh, here we go. So here's a mass spectrometer. Fire this sucker out of here. Boom. Shoot. Now this is the voltage because they're basing this on the energy. 1/2 mv squared is equal to EV. Okay. So if I want to set the mass, so we got mv over EB, and then by pulling this guy for 1/2 mv squared, I can get rid of the speed. Okay? All right. Right, we're going, well, how do we get from there to there? Don't worry about it. I never use that anyway. I mostly use this guy for our problems. And here's shows different isotopes where they're hitting the most. Okay, so I'm going to stop there.